Hey guys, welcome back to the second video on molecular orbitals. We're going to be going to a few more examples just so you guys get some better practice and also go through some things that you guys may see that you may think is a little bit tricky, but hopefully this can clear some stuff up for you guys. So in the previous video, we looked at butadiene. This guy right here, 4 carbons and the 2 double bonds. So now what I want to do is I want to ask you guys a question, right? When we looked at butadiene, we saw that it had 4 pi orbitals, 4 p orbitals, right? So what about this system? What if I gave you guys this molecule right here, 3 carbons, 1 double bond, and a positive charge? Okay, so what exactly are we going to do here? What I want you guys to try to maybe pause the video and figure out is how many p orbitals do we have in this allylic cation? Okay, think about that for a second. All right, pause the video and then unpause and we'll figure it out. All right, guys, so I'm going to assume you just pause the video, try to figure it out. So what I'm going to do is I'm going to look at the resonance for this guy. But actually, before I even do that, the trickiest part here is probably that plus charge, right? It was probably easier for you to figure out that we have at least 2 p orbitals here, right? But we're not sure about that carbon with the plus charge, right? So what I'm going to do is I'm going to just draw the resonance structures. Move this double bond over. And we're going to get this guy right here. The double bond's now here. So what about the p orbitals now here? You can draw them this way. And now if I look at the original compound, I'll just redraw them again. So we weren't sure about this carbon, and you can kind of see that we were able to move the double bond and get an orbital on here, right? And so all that we were dealing with, remember, is a conjugated system, right? Where all the p orbitals here can overlap with each other. So this can allow resonance here. And so if you look at butadiene, right, this is the major resonance form, but we can still draw something by putting those electrons on that carbon, right? And then moving this over here, giving us this resonance structure. A negative charge here because there's lone pairs now there. The double bonds here and the plus charge there. But we can still resonate all 4 of those carbons through all 4 of the p orbitals. And we can do the same for this cation. And so we actually have 3 p orbitals here. Okay, not 2, but 3. So what we're going to do is we're going to draw the p orbitals for this cation. So we have 3 p orbitals, and remember the trick I said before in the previous videos, the way I like to do this is I like to draw the molecular orbital with the lowest energy, which is 0 nodes, and then the one with the highest energy, which is going to be the maximum amount of nodes first. All right, so remember the lowest energy one is always pi 1. We have 3 p orbitals, so draw 3 little balloon animals. Here's 3. And here's our little line for where the electrons are going to go. So remember the lowest energy one, we have 0 nodes. That means all p orbitals overlap. Okay? So now we have this. And now we're going to draw the one with the maximum amount of nodes. How many nodes is that? It's always 1 less than the amount of p orbitals you have. So we have 3. So the highest molecular orbital one is going to have 2 nodes, right? And so this guy's going to have 0 nodes. We're going to have another one with 1 node, and the highest one is going to have 2 nodes, right? So that's going to be pi 2 here. Pi 3 is our highest. Here's our balloons. So now, in the highest energy one, we have the maximum amount of nodes, and none of the orbitals overlap. So I'm going to shade this one white, then this one down. The white is going to be at the bottom, and then this one is going to be at the top. And so remember, we always draw a node where we do not have overlap. So right here and right here, this is going to be the highest energy. So remember, energy, which I'm going to just write as E increases as we go up. So those are the easiest ones. And now we have to draw our middle one. So let's just draw these empty, and then we'll figure out how we shade them. So remember, we need to keep our nodes, not our nodes, sorry. We need to keep our molecular orbitals symmetrical. So where we put our one node, if I put it here, shade this guy over here, but now it's going to be this way. So you see one on the left is going to be shaded white at the top, and the two on the right are downward white. That doesn't work. Neither would it work if we put it here, right? And we can't put it on the outside because there's nothing on the other side of it. So what we're going to do is we're going to put the node through the orbital, okay? You may see this as a dashed line or a line through an orbital, or it could be just like an empty space with a dashed line through it, or maybe like a dot. Sometimes you'll see those, all right? But I'm just going to leave the orbital and like this, and we're going to have that dash line through it just to keep you guys comfortable so that you still know we have 3 p orbitals total. So that's how you draw it. Usually when you have an odd number of p orbitals, you're going to end up having to draw nodes through your, it's going to have to go through the compound. Not through the compound, sorry, through a p orbital. All right, so don't get nervous if you think that that's what you have to do, because that does in fact happen. All right, usually with the odd numbered p orbitals. All right, and so now how are we going to shade this guy? Well, I'm just going to shade this one white. I always like to usually shade the first p orbital that way, just a habit. And so now what we're going to do is, if we don't shade this guy, he's got a node, right? It's almost as if I erased him and left it blank. You don't shade it, but he still acts as a node. So that means this one that will have to be shaded this way, okay? So now we have all 3 of our molecular orbitals, and we're going to fill in the electrons. So how many electrons do we have? Here's our compound. We have 3 p orbitals, 1 electron for that carbon, 1 electron for that carbon, but this guy is a cation. No electrons there. Even if you looked at the resonance structure, 1 still empty and 2 filled. So we have 2 electrons total. So remember, we always put 2 electrons per row, and we always fill up an entire row before we go to the next one, and we always start at the bottom. 1 electron, 2 electrons. Okay, so that's as far as we can go. And now remember, we want to figure out what the HOMO and the LUMO orbitals are: the highest occupied molecular orbital and the lowest unoccupied molecular orbital. Okay, so remember what is the highest occupied molecular orbital? This is the orbital. This is the highest orbital on our, the highest row you can think of that has the electrons. In this case, it's our bottom row. So this is the HOMO. The LUMO is the lowest row, the lowest unoccupied molecular orbital with no electrons at all. So it's going to be this one right here, pi 2. So that's the HOMO and the LUMO. Now we're going to go on to another example, because this example is done. I hope this wasn't too bad for you guys. We're going to go on to a similar example. All right, but what we did at first, we did the allylic cation. Now we're going to go on to this example. Similar, but now it's a radical, the allylic radical. Okay, so remember, we still have a conjugated system here. I can form a double bond right along these 2 carbons by using some, remember, radical arrows. Let me just fix this here. 1 arrow. Oh, it should be better this way. Okay. And the way we would draw that is we go like this. Here's your double bond, and we have the new radical right there, right? Because we use this 1 electron as one of the electrons for this double bond, and one of them from here to form 2 electrons in that double bond. And the 1 electron on this double bond is now here. Okay? And so because we can move through 3 carbons technically, we have 3 p orbitals. It's all conjugated to each other. All right, we can flow the electrons through those 3 carbons, 3 p orbitals. So now we're going to draw our orbitals. So starting with, again, always the lowest energy one, the one with 0 nodes. Remember, this is 0 nodes, so everything overlaps. Easiest one to draw. We're going to have another orbital with 1 node. So 0 node, 1 nodes, or 1 node. And now remember, we always, the maximum amount of molecular orbitals we draw is always until we have the amount of nodes that's 1 less than the p orbitals. We have 3 p orbitals. Subtract 1, we get 2. So we're going to go until we have 2 nodes, which is pi 3. So that's 2 nodes. Okay? And so the highest energy one is always, again, the second easiest to draw, where nothing overlaps. So we're going to draw this shaded white up at the top, this one shaded white at the bottom, this one shaded white at the top. And remember, we always put a node where things do not in between where things don't overlap. Right here, and right here. And again, always make sure that your that the molecular orbitals are symmetrical, always. So that's 2 of our orbitals. We just need to fill in the middle one. So let's draw the 3. Now we need to put 1 node. So again, we need to keep it symmetrical, so I can't put it there, and I can't put it there. Again, this is going to be a case where we put it through the middle of the orbital. And now we're going to fill this guy in white at the top, this guy in white at the bottom. So you see that the orbitals actually are the same as the previous guy. Oh, no, the radical are the same as the cation, right? The difference between these guys are going to be in the electrons, how we distribute the electrons. So how many electrons do we have? Well, in this double bond, we have 1 here, a second one here, and the third one. When we did the cation, we had 2 electrons for that double bond, but then 0 here. So we have 2 electrons for the cation, but 3 for the radical. So now again, let's fill up our orbitals. 2 here, and now 1 over there. Right? We have 3, so we stop at 3. So now let's do our HOMO and our LUMO. The highest orbital with electrons is the one with pi 2, right? Because it has 1 electron. 1 electron is still an electron, so don't think, oh, you need the full pair. Nope. If you have 1, that is now the HOMO. And the lowest unoccupied molecular orbital is now going to be this guy right here, LUMO. Before, remember, with the cation, this was our HOMO, pi 1, and our LUMO was pi 2. All right? And now the last example with this, like, the ones that are weird kind of is going to be, instead of a cation or a radical, it's going to be an anion. All right? So we have this. And actually, what we're going to do, since remember how the orbitals are going to actually be the same, the only difference in between these 3 examples are how we distribute the electrons. So here's a radical. First, let's figure out if it's conjugated or not. Right? We have 3 carbons, so let's see if we can distribute the electrons across all 3. You can bring that lone pair down. Right, here's your lone pair. Put it, and now put a lone pair on this carbon. You're going to get double bond here, and a lone pair now on that carbon, so there's your negative charge. So you can see, we can flow those electrons through all of those 3 carbons, so it's a conjugated system. Therefore, we have 3 p orbitals because we can flow through all 3 carbons. Okay? So now how many electrons do we have? So let's clean this up first, just so we have some room. So we have 2 electrons from the double bond, and because remember, carbon with a negative charge usually means we have a lone pair, right? And because here, if I didn't include this, we have the carbon is bound to that carbon, that's one bond, and it's also going to be bound to two hydrogens and the lone pair. That's a total of 4 bonds, and that because carbon is neutral with 4 bonds, but we have how many electrons? One here, 2, 3, 4, 5 in terms of formal charge. So we're going to have a negative charge, right? And so in this case now, we're going to have 4 electrons. Cation, we had 2. Radical, we had 3. Now we have 4. So let's put in the electrons. So we're going to have 2 here, and now 2 over there. So now what are our HOMO and our LUMO? The highest occupied molecular orbital, remember the row with the highest row with electrons is this one, pi 2. The lowest row without electrons is our LUMO. This is going to be pi 3. So same as the radical. So that's how we do these 3 examples. All right. Now remember, this is just an example where we used 3 carbons. This can go further than that. Okay. We can have bigger examples. So don't limit yourself to this, just these 3 examples in terms of 3 carbons only. Let's go through this example right now. Right? So this is going to be a pentadienyl cation. Right? We have 1, 2, 3, 4, 5 carbons, and we have a diene. That's why we write dienyl. So how do we draw this? So we have 5 carbons. How many p orbitals do we have? Well, we have this cation here and 2 double bonds. So let's see if I can, if the system is conjugated across all 5 carbons. We can look at resonance. Move this double bond here, and I could bring this guy there. And now he's going to have the cation here. So you can see electrons were able to move through all 5 carbons. So that means we have 5 p orbitals. Okay? So let's draw all the orbitals. So we're going to have 5. We have 5 p orbitals. So let's draw that out first. That's going to be pi 1, 1, 2, 3, 4, 5, and the little space for the electrons. Remember, the trick is always to draw the lowest energy one first, the one with 0 nodes. I'm going to have to move this down because we're going to need some room. Okay, so 0 nodes. And remember, if we have 0 nodes, everything is overlapping. So fill it all in across the board. Okay, and so that's the easiest one to draw. Now, remember, we always keep going until we have the amount of nodes. That's a molecular orbital with the amount of nodes, 1 less than the amount of p orbitals. 5 p orbitals, 4 nodes is the maximum. So we're going to keep going until we have pi 2. He's going to have 1 node. Pi 3. He's going to have 2 nodes. Pi 4. He's going to have 3 nodes. And let me just move this. Pi 5. He's going to have 4 nodes, our maximum. All right? And so now, let's go and draw the highest energy one first, the one where nothing overlaps. That's always the second easiest to draw. And I'm just going to copy these over. All right, and so remember, nothing is going to overlap when we have the maximum amount of nodes. And so I'm going to draw this guy is going to be a shade of white, this one down, up, down, up. And so you can see we always put the node in between where something doesn't overlap. 4 nodes. All right. Now we have to draw the 3 remaining. So here's our next set. And so remember, we have to draw one node but keep it symmetrical. So what happens? Where am I going to put the one node? Here? Well, then I'll have 2 on the left and 3 on the right. Not symmetrical. Here? Nope, can't do that either, because that's also not going to be symmetrical. Can't do it here, and I can't do it here. Okay, this is going to be, again, a case where we have to draw the node right through a p orbital. Right through this guy. Those are one node. So now let's shade. White at the top, white at the top. Skip this guy with the node, and we, again, switch. So there's your p orbital, your molecular orbital with one node. Let's go again now and draw 2 nodes. Okay? And so, where are we going to put 2 nodes? Well, we're going to have to go and put these through 2 carbons again. Right here. And right here. Alright? And that's how we have this guy. And now, the last one, we're going to have 3 nodes. We're going to put it 1 through here. Oh, I'm sorry, my mistake. We're going to put it right through the middle one again, and now we got 2 nodes left. And we're going to put 1 right here, and 1 right there. So this one is going to be white at the top, white there. This guy goes up here, and we bring this one down there. And so those are our 5 molecular orbitals. You can see we have to keep it always symmetrical. Okay? And so you guys can see also that the nodes kind of look like a pyramid, an inverted pyramid or triangle, getting larger as we go up. All right? Spread further out. Now let's fill in the electrons. How many do we have? 1 here, 2, 3, 4, and the cation doesn't give us any, so only 4. So let's fill them in. Always 2 first. We always go fill up an entire row, and a row can only hold 2. So that's 2 and 2 over there. Now let's figure out our HOMO and our LUMO. So the HOMO is the highest occupied molecular orbital. That's going to be pi 2. Our LUMO is the lowest unoccupied molecular orbital, pi 3. All right? And so that's another example where you can have stuff like this. Now, again, they could ask you to draw the molecular orbitals where we have a compound like this. 3 double bonds, and you do it the same way. How many orbitals, p orbitals do we have here? We're going to have 6. How many electrons do we have here? Also 6. All right, so it's going to be a little bit more tedious, but you know, it's all the same sort of idea. So in the next video, we're going to be going over how we do, we're going to go over more things about these conjugated dienes, right, and some properties about them, right, and I'll see you in the next video.